We rely on our power grid for literally everything. Our lights, our computers, our whole society. But what if a single, invisible attack could shut it all down? Today, we're going to dive into some really fascinating research that tackles one of the biggest hidden threats to our modern world.
Picture this. One blast high up in the sky and an entire continent just goes dark. It sounds like something straight out of a movie, right? But believe it or not, this isn't science fiction. This is a very real threat that some of the world's top engineers are trying to solve right now.
So, what's the culprit? It's something called a High-Altitude Electromagnetic Pulse, or HEMP for short. The idea is you detonate a nuclear weapon way up in the atmosphere. The blast itself doesn't touch the ground, but it unleashes this massive, invisible wave of electromagnetic energy that can literally fry electronics across thousands of miles.
Now here's where it gets really interesting. HEMP isn't just one single massive zap. Nope. It's actually a sequence of 3 very different pulses, and they all happen faster than you can blink.
First up, you've got the E1 pulse. That's the super fast, super intense burst of energy. Then comes the E2 pulse, which is kind of like a widespread lightning strike. But the real danger, and the thing these researchers are focused on, is the E3 pulse. This one's different. It's slow, a low-frequency wave that acts like a massive DC current, flooding the power lines and just completely overwhelming the huge transformers that are the backbone of our entire grid.
And if you think this is all just theory, well, think again. Back in 1962, the U.S. did a high-altitude nuclear test called Starfish Prime. It was detonated over the Pacific Ocean, and it knocked out streetlights and caused electrical damage in Hawaii from 800 miles away. And that was 60 years ago. Just imagine what something like that could do to our hyper-connected grid today.
So the big question is, how on earth do you defend against a threat that's so widespread? Well, the researchers behind this paper did something really clever. Instead of just trying to build a bigger shield, they decided to think like the enemy. They wanted to figure out how a HEMP actually turns our own grid against itself.
Here's a cool way to think about it. Imagine the HMP is a puppeteer, and our power grid is the puppet. The electromagnetic pulse is pulling on the strings, our transmission lines, trying to make the whole system go haywire. So the goal isn't to build a giant fortress around the puppet. It's to figure out which specific strings you need to cut to stop the puppeteer.
Okay, but before we get to that elegant solution, let's talk about the obvious one, the brute force approach. The one where you just try to armor plate everything. If you see a HEMP as this unstoppable force, then defending against it starts to look like a monumental, almost impossible task.
So, in the theoretical model grid the researchers used, which has 15 transformers, the standard thinking says you have to protect all 15 transmission lines. Every single one. You can probably see the problem here, right? We're talking about a massive and likely outrageously expensive undertaking.
All right, so what if you try a different angle? Maybe protect the transformer's ground connections instead? Well, even then, the theory dictates that you need to secure 14 out of the 15 paths. We're still stuck in this world of a costly, complex, brute force solution.
But this is where the research takes a fascinating turn. This is the pivot. The team realized that this protect everything model was just way too rigid, and that realization opened the door for a much smarter strategy. The key insight was to completely reframe the problem. Look, the goal isn't perfect, total immunity. That's probably impossible. The real goal is just to prevent a catastrophic failure. And for the grid, that means stopping the transformers from saturating, which is basically when they get so overloaded with current that they overheat and fail. As long as you can keep them operating in a safe zone, you've won.
So to test this new approach, the researchers simulated 2 different defense strategies. First, there's local control. That's where each protective device is on its own. It only sees what's happening right there. And then there's global control. That's the team effort, where all the protective devices talk to each other and coordinated defense across the entire grid.
So what happens when you shift from pure theory to a realistic simulation that's just focused on preventing those transformers from going critical? Well, the number of protective devices you actually need is kind of staggering.
And here it is. This is the big aha moment. Remember the brute force theory that said you had to protect all 15 transmission lines? The simulation showed that with a smart, globally controlled system, you only need 3 strategically placed devices. Just 3. That's an 80% reduction in what was thought to be necessary. That's a game changer.
This table really tells the whole story. Global control is just way more efficient. For transmission lines, it takes the number of devices you need from 11 all the way down to just 3. The data also shows that protecting the lines themselves is a more effective strategy than protecting the transformer neutrals. A smart, coordinated defense is the undisputed champion here. It's not even close.
But the insights didn't stop there. As the researchers dug into why global control was so effective, they uncovered a really surprising paradox about our power grid.
Get this. To run that super effective global control system, how many sensors do you need to monitor the entire grid? The answer is astounding. Just one. I know, it sounds crazy, right? But because the grid is so interconnected, a single measurement, when combined with a precise model of the grid, can actually tell you the state of the whole system. The very connectivity that creates the vulnerability also creates perfect observability.
Now, of course, there's a big catch. Relying on a single sensor is a high-risk game. It creates a massive single point of failure, and it assumes your model of the grid is absolutely perfect, which in the real world it never is. So in practice, you'd obviously want multiple sensors for redundancy and safety.
The key takeaway from all of this is that protecting our infrastructure isn't just about building bigger walls. It's about building smarter defenses. By truly understanding the system and the threat, we can move from these clunky brute force tactics to elegant, targeted solutions. And that leaves us with a final thought. What other complex problems could we solve, not with more resources, but with a deeper understanding?